Welcome to the Deep Dive. If you're trying to stay ahead of the curve in fundamental machine learning research, you know that this time of year means one thing: the annual research flood known as NeurIPS.
It is the absolute epicenter of knowledge sharing. We're talking about the 39th Annual Conference on Neural Information Processing Systems, and this year it's in San Diego, California.
With a satellite event too, right?
That's right, a necessary one stretching down to Mexico City. I mean, every major finding in neural networks and computation, it's presented here.
And when that flood hits, it's overwhelming. So our mission today is very specific, designed to give you, our listener, a critical shortcut.
A filter.
Exactly. We're sifting through the massive stack of papers and presentations from one of those consequential industry participants, Apple, to figure out where the true frontiers of AI research are being pushed.
And that's such a valuable lens because when a company of this scale shares its fundamental non-product research, it really does set the agenda for the whole field.
It provides a unique window. As you said, this isn't about new device features.
Not at all. It's about the underlying mathematical and theoretical breakthroughs, the stuff that's going to define the AI systems of, 2027 and beyond.
So to make sense of it all, we've organized their contributions into four critical themes, four areas that really show the core challenges the industry is solving right now.
Let's call them the four foundational pillars of this deep dive.
I like that. Okay, pillar one. Advancing privacy-preserving machine learning. This is about making guarantees about data security that are mathematically ironclad.
Then pillar two, rigorously understanding reasoning models' capabilities and, maybe more importantly, exposing their fundamental limitations when they're faced with genuine high-level complexity.
Pillar three is all about generative AI. Looking at new innovative approaches that specifically challenge the high computational cost of the current dominant methods like diffusion models.
And pillar four, a topic that directly impacts the billions of dollars spent on these huge models, the science of scale. Specifically, a systematic, principled way to figure out the optimal mix of training data using universal scaling laws.
So these four pillars, they really paint a complete picture of where ML is right now. Foundational security, cognitive capability, creative output, and of course, economic efficiency.
A perfect summary.
All right, let's unpack this. We have to start right at the core, with the bedrock of trust, privacy.
So getting into this first pillar, the source material is very, very clear. This research starts with the premise that privacy is a fundamental human right.
Right, and that means you have to rely on robust mathematical guarantees.
Not just, some vague policy safeguards.
Exactly. We're talking about things like differential privacy, where you add measured mathematical noise to guarantee that no single person's input can be inferred from the final model.
But that creates a tension, doesn't it? You're adding noise, you're obscuring the data to protect the user. That must mean the model loses some utility or accuracy.
That's absolutely the core trade-off. And the whole goal of this cutting-edge research is to minimize that sacrifice. Which brings us to the first spotlight paper, Instance Optimality for Private KL Distribution Estimation. Okay, that title is a mouthful. But the task it's describing is surprisingly universal.
It is. At its heart, it's just about accurately estimating a discrete distribution from a set of samples.
So why should our listener care about that? Why is that task so fundamental?
Because distribution estimation is, it's the invisible backbone of modern computing. It governs how we compress data efficiently, how language models estimate the probability of the next word.
How your speech recognition figures out what you just said.
Exactly. It's figuring out the most likely sequence of sounds. If you can't estimate that true underlying distribution accurately, the whole system just falters.
Okay, and in this paper, they're measuring the accuracy of that estimation using Kullback-Leibler divergence, or KL divergence. We hear that term a lot, but why KL divergence specifically? Why not a simpler metric?
Well, KL divergence is a really essential choice here because it's a non-symmetric measure, and crucially, it actively promotes diversity and smoothness in the estimated distribution.
So it pushes the model to be more comprehensive.
In a way, yeah. It penalizes you heavily if your estimate deviates a lot in regions where the true distribution is important. So in practical terms, it forces the model to be robust, to understand the structure of the data deeply, rather than just overfitting to a few rare data points.
Got it. So we have a fundamental task and a high-fidelity measurement. Now let's get to the real innovation. Instance optimality.
Yeah.
What is that? And why is it so hard to achieve under differential privacy?
Okay, so when you design a standard algorithm, you often aim for it to be minimax optimal. That's Well, it's the best result you can guarantee for the worst case
A
scenario.
general purpose solution.
Right. Instance optimality is way more ambitious. It means the algorithm is designed to adapt to the specifics of the data set it's given. It performs almost as well as the absolute best, most specialized algorithm you could have possibly designed, only for that unique instance of data.
Wow. Okay, so it's maximum efficiency tailored to the exact input. But when you layer on differential privacy, which forces you to add random noise,
Yeah.
doesn't that just destroy the possibility of doing that?
That is the central tension they are solving.
How can you tailor a solution perfectly to the data if you are literally mandated to obscure that same data?
Right, that's the puzzle. Differential privacy requires that the algorithm's output barely changes when you add or remove one data point. It has to be insensitive. But instance optimality needs the algorithm to be highly sensitive to the subtle structure of that specific data set.
And historically, the noise you needed for privacy just washed out all those subtle structures.
Exactly. What these researchers did was design new algorithms that use adaptive noise mechanisms. They're smart enough to look at the dataset's characteristics and apply the minimum required noise in just the right ways,
So they can satisfy the privacy bound.
while still extracting that instance-specific information they need for the KL optimization.
That's incredible.
It is. They provided new mathematical bounds and shared the algorithms that achieve this balance. They've proved that you don't have to sacrifice this high degree of optimized performance just to get differential privacy.
So if we go back to the language model example, this means the probability of the next word, even when calculated privately, can be almost as accurate as if it were calculated using fully exposed data.
That is a massive leap for secure model deployment.
And a perfect segue to the second privacy paper.
It is, yeah. It connects seamlessly to privacy amplification by random allocation. This one delves into making the mechanism of differential privacy itself more efficient.
We already know differential privacy relies on randomization to make individual contributions ambiguous. So what kind of randomization are they studying here?
The focus is on a specific sampling strategy called random allocation. This is a technique you use during the training process. So imagine the entire training is a sequence of, say, computational steps.
100 steps, for example.
Right. In random allocation, a user's data point isn't used in all 100 steps. Instead, it's only used in a specific number. Let's call it T steps, say 10. And those 10 steps are chosen randomly and uniformly from the entire sequence.
So if I contribute my data to a big federated learning model, maybe my data only participates in 10 of the 100 training steps, and which 10 is decided by a coin flip, essentially.
Exactly. Now, on the surface, that sounds like it might reduce the model's utility, but the magic is in the privacy benefit. By adding that extra layer of randomness, the uncertainty of when your data is used, you fundamentally amplify the privacy guarantee. An attacker has a much harder time linking the model's final state back to your specific input.
Okay, I get the mechanism. But why is it so important to have a theoretical guarantee for this? Couldn't practitioners just use it and see that it works? Why do we need the formal proof?
This is crucial. It's because privacy systems are built on something called the composition theorem. When you run an algorithm for many steps, the privacy cost adds up. It composes.
So 100 private steps has a much higher privacy cost than just one.
Much higher. And researchers rely on these composition theorems to put an upper bound on that total cost, which in turn dictates how much noise they have to add. The more accurately you can model that composition.
The less conservative you have to be with the noise.
Precisely. The random allocation mechanism inherently slows down the rate at which that privacy cost accumulates. The chance of an attacker seeing your data across multiple linked steps is just reduced dramatically by the random sampling. So what the Apple researchers did was provide the first comprehensive theoretical guarantees and numerical estimation algorithms for this specific scheme.
So because they can mathematically prove the exact amount of privacy amplification you get from this K out of tech sampling, they now have a tighter bound for the composition theorem.
And that's the win for utility. A tighter bound means you can afford to add less overall noise while still satisfying the strict differential privacy rules.
Less noise means a more accurate model. A better privacy utility trade-off.
That's it. And the source mentioned this has a huge practical impact on, and I'm quoting, a host of important algorithms.
Right, let's ground that. Where would we see this in the real world?
You see this sampling strategy most often in large-scale distributed training, especially federated learning, where lots of user devices contribute updates. So this analysis directly improves the foundations for things like differentially private stochastic gradient descent, or DPSGD.
Which is the backbone of private model training.
It is. And it also impacts aggregation schemes. When you have thousands of devices sending updates, you have to securely aggregate them without exposing any single contribution. This research provides a better foundation for that.
So another paper they mentioned, preamble.
Yes, preamble. Private and efficient aggregation via block sparse vectors. That system is designed to handle tons of sparse updates from clients. The tighter privacy bounds from this random allocation paper are essential for making a system like preamble practical and accurate enough for the real world.
So it's a clear line from abstract math.
Directly to superior deployable engineering. It's a fantastic example.
A remarkable demonstration. Okay, we've established how to protect the data foundation. Now let's move on to what's built on that foundation. Cognitive capability or reasoning. All right, we're shifting gears now. We're moving from the mathematical guarantees of privacy to pillar 2, the complex cognitive tasks AI systems are trying to do. And reasoning, I mean, that's the holy grail, right?
It really is. It's the ability for an AI to accomplish complex, multi-step objectives, solving advanced math, generating bug-free code, controlling a robot.
And the hype around large language models often suggests we're already there, that we have general-purpose reasoning.
Right, but this research, it really investigates the underlying mechanism. In one of the papers, The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models, suggests that the complexity we see, well, it might be hiding a fundamental fragility.
And research that tries to expose limitations is often the most valuable. It tells us exactly where we need to focus our efforts next.
I agree completely. And the way they did it here was so rigorous. This wasn't just testing models on existing, messy public data sets.
No.
No, that was the big methodological breakthrough. They used custom, controllable puzzle environments. You can think of it as a highly calibrated laboratory for AI cognition.
A lab setup.
Okay.
Okay, and why is controlling the complexity variable so critical here?
Because in real-world benchmarks, complexity is often a big, messy ball of, linguistic difficulty, knowledge retrieval, and logical steps all tangled together. By using these puzzles, they could isolate the variable of required reasoning depth.
I see. But the most crucial part you're saying was being able to verify more than just the final answer.
Exactly. They could verify the intermediate reasoning traces, the model's step-by-step work.
The AI's scratchpad. Why is that the key difference? How does seeing the intermediate steps let you diagnose its thinking?
Well, think about it. When a model generates a solution path, a chain of thought, and it's wrong, traditional evaluation just says wrong answer. Right. But by tracing the steps, they could pinpoint where it went wrong. Was it a planning failure at step 1, a logical error at step 5? Or did it just run out of capacity to even structure the task? It moves the diagnosis from just performance metrics into cognitive structure.
Okay, so they run these tests focusing on what they call frontier large reasoning models, or LRMs.
Models specifically optimized for this kind of multi-step logic.
Right. And what was the primary finding?
The key finding was stark. The accuracy of these LRMs does not degrade gracefully. It collapses.
Collapses.
Dramatically. Beyond certain, and I should say relatively modest, complexity thresholds, it's not a slow decline in performance, it's an abrupt systemic failure. The illusion just shatters at a specific point of difficulty.
Which suggests the ability isn't a continuous, scalable skill. It's more like a fragile structure that just breaks when you push it too far.
That's a great way to put it. And they did compare these specialized LRMs against general-purpose large language models, LLMs.
Making sure it was a fair fight.
Absolutely. They ensured the models had equal inference compute budgets, so it was a true apples-to-apples comparison. And the complexity curve they mapped out was really fascinating.
Okay, walk us through that curve.
For the low-complexity tasks, things that required good pattern matching, simple retrieval, the general LLMs actually slightly outperformed the LRMs.
Interesting. So general knowledge wins when the lift is light.
Correct. It suggests the breadth of the LLM's training is more efficient for simple stuff, but as complexity moved into the medium range, the specialized LRMs showed a clear, measurable advantage. They were doing what they were designed to do.
Okay, but where did they hit the wall?
That's the most critical finding. When the complexity moved into the high range requiring abstract multi-level planning, both types of models failed.
Both of them.
Both of them. The reasoning capabilities, despite the specialization and the massive size, they just weren't robust enough to handle that abstract complexity. It raises really profound questions about what we're actually measuring when we talk about AI reasoning.
It sounds less like human intelligence and more like a high-performance machine running an algorithm that has a hard, predetermined operational limit.
The data certainly supports that interpretation. And adding another layer of mystery to this is what they called the surprising effort paradox.
Okay.
So when the problems got harder, the LRMs initially showed increased reasoning effort. Longer chains of thought, more tokens used. They were demonstrably trying harder.
Which is what you'd expect. Harder problem, more work.
But once the problem complexity passed that known failure threshold, the point where accuracy collapsed, the model's reasoning efforts suddenly and unexpectedly declined.
It went down.
It went down. The chain of thought got shorter, less structured, often nonsensical. And this happened even when the models had plenty of token budget left. It wasn't a memory issue.
That's what makes it a paradox. It's not a resource failure, it's a structural one. It's almost like the model realized the problem was unsolvable with its current architecture and just gave up.
It suggests that once the required complexity gets too high, the model doesn't just struggle to execute the steps. It fundamentally loses the ability to even formulate the required steps in the first place.
That failure mode is completely different from a normal computational error.
Completely. And it means we need entirely new approaches to overcome it. We can't just scale our way out of this problem.
How does this square with all the success we see with large models in coding or math? Are those just illusions too?
I'd say those successes are often highly complex pattern matching applied to problems that fall within that medium complexity band. What this research shows is that true, novel, abstract reasoning is still profoundly limited.
So the takeaway is we need new architectures, not just bigger models.
Exactly. Architectures targeted at planning, decomposition, and state space management. And the research team underlined this with an expo talk.
Right, on December 2nd.
Yeah, and the talk really drove home the point that current evaluations of reasoning can be profoundly misleading. If you only look at the final score on a benchmark, you miss the systemic failure happening beneath the surface.
So the crucial insight for you, the listener, is that AI reasoning isn't just about what models answer. Critically, it's about how they try to solve problems. And until we can solve that effort paradox and the accuracy collapse, we are still a long way from general, scalable reasoning. Okay, so the journey from privacy and the limits of cognition now takes us to Pillar 3, generative AI, the creative frontier. And we've seen just breathtaking progress in high-res image generation.
We have, but as the source material highlights, the dominant methods, diffusion models, autoregressive models, they come with a massive computational ceiling.
A huge cost.
A huge cost. Diffusion models require so many sequential steps, which makes inference slow and energy intensive. Autoregressive models, while great for text, are just really slow for images. The field desperately needs a high-quality alternative that is also efficient and rigorous.
And that alternative is presented in this next spotlight paper. STARFlow, scaling latent normalizing flows for high-resolution image synthesis. So this is all about normalizing flows, or NFs.
Yes, and NFs have historically struggled to compete with diffusion models at that high-resolution, high-quality scale.
So what are they? Why have they always been the mathematical darling of the generative world?
Well, a normalizing flow is a generative model that learns a complex, and this is the key, invertible transformation. It learns to map a simple, known distribution, like Gaussian noise, into a complex data distribution, like realistic images.
Okay, why is that invertibility so powerful?
Invertibility gives you two amazing things. First, sampling and encoding are deterministic and efficient. But second, and this is the most important part, it allows for exact likelihood modeling.
So unlike diffusion models, which approximate the data's probability distribution.
With NFs, you can calculate the exact probability of any generated data point.
And if you can calculate the exact likelihood, that's invaluable for anything requiring model certainty, anomaly detection, medical imaging.
Or ensuring generated output aligns precisely with safety parameters.
Absolutely.
Exact likelihood is a gold standard. The problem has always been that the architecture of NFs involves calculating this thing called the Jacobian determinant during training, which is a computationally heavy step that stopped them from scaling to high resolutions.
So the breakthrough in STARFlow isn't the concept of normalizing flows, it's the scaling part. How did they get around that computational burden?
STARFlow builds on an earlier architecture called TARFlow, which kind of combines the sequential power of transformers with the rigor of NFs. The innovation was in optimizing the latent space architecture and applying some very sophisticated parallelization techniques to handle the massive input dimensions you need for high-res images. They basically managed to sidestep that Jacobian bottleneck.
So they finally figured out how to scale the flow. What kind of quality are we talking about now?
STARFlow is now producing images at resolutions and visual quality that were previously thought to be unreachable for NF models. The source emphasizes that it now rivals top diffusion and autoregressive methods. Yeah. The reference to their Figure 2, which shows samples with variable aspect ratios, highlights that the method is also flexible and robust.
So we finally have a high-res, high-quality generative technique that maintains that exact likelihood modeling.
And offers faster inference than the dominant models. It's a massive architectural win. It really validates normalizing flows as a major force in the generative world.
Okay, so great generation is one thing, but controlling it is another. We need to be able to steer these models, whether it's for safety or for style. And that brings us to the second generative paper, LinEAS, end-to-end learning of activation steering.
Right. The demand for efficient, high-quality control is just growing every day. We need methods to ensure these models are safe and follow user directions without having to do costly fine-tuning or needing huge labeled datasets.
And the core idea here is activation steering. So instead of retraining the model weights, you intervene on the model's intermediate numerical steps, the activations.
Exactly. You're correcting the model mid-thought. You identify the distributional difference in activations between a source prompt set, like toxic outputs, and a target prompt set, the desired outputs. And then you train a small, lightweight correction map to steer the source toward the target.
So what does linear end-to-end activation steering add to this? What's the innovation?
The key innovation is the training mechanism. Older steering methods often trained these correction maps layer by layer, kind of optimizing locally. LinEAS is trained with a global loss function,
A global loss.
meaning the optimization accounts for all the layer-wise shifts across the entire model structure all at once.
That sounds way more efficient.
Yeah.
How did that translate into performance gains for a practitioner?
It leads to efficiency gains that are just honestly astonishing. First, the data efficiency. LinEAS requires only a handful of unpaired samples to be effective. We're talking maybe 10 or 20 examples of bad output and 10 or 20 examples of good output, not thousands.
A handful of samples to control a massive foundation model. That's a game changer. It makes controlling these things accessible to smaller teams or for niche applications.
Absolutely. And moreover, the global framework allows for sparsity regularization.
I mean,
It's a technique that forces the learned steering maps to be minimal, so the intervention becomes surgically precise. It only activates in the specific parts of the model that are strictly necessary to make the change.
so you're not hitting it with a sledgehammer, it's a scalpel. You preserve the base model's fluency everywhere else.
Precisely. When you steer the model away from toxicity, you don't accidentally degrade its ability to write code or poetry. The research shows LinEAS outperforms existing methods in things like toxicity mitigation.
And because the method is modality agnostic, it works for images too, right?
Yes. They showed fine-grained control for style induction or object removal in text-to-image models. It is a huge step toward making generative models safe, highly customizable, and affordable to control. And that leads us perfectly into Pillar 4, which addresses arguably the biggest economic and logistical challenge in training these models, the science of scale and efficiency.
Right. This is where we talk about the massive upfront cost of ML. I mean, we all know the performance of these huge models, models trained on text, code, images. It depends critically on the data mixture.
It does. And if you're training a massive multimodal model, how do you decide the right proportion of web text versus code versus image caption pair?
This is a standard approach now.
Currently, it's often an educated guess followed by prohibitively expensive trial and error. You pick a ratio, you run a multi-million-dollar training run for weeks, and then you evaluate. If it's not great, you try again with a different ratio, burning just immense amounts of compute. The source material calls this impractical for large-scale pre-training, which is an understatement.
When a single run can cost in the high 7 or even 8 figures, your margin for error is 0. We need a predictive science, not trial and error engineering.
And that's exactly what this paper, Scaling Laws for Optimal Data Mixtures, delivers. It provides a systematic, principled method using scaling laws to determine the optimal data mixture for any target domain before you commit to the massive training run.
Okay, let's get into the core formula. What are the variables this scaling law relates, and what does it predict?
The law predicts the model loss, basically how well the model performs, as a function of three critical variables. First, model size, which is n, the number of parameters.
Got it.
Second, the number of training tokens, which is d, the total data budget. And third, the domain weights, or the mixture itself, which they call h.
So if I plan to spend my compute budget to build a 50 billion parameter model N and train it on 10 trillion tokens, D, the scaling law can tell me exactly what percentage of code versus prose H will give me the lowest possible loss.
That is the predictive power they unlocked. And the research established something critical about these laws. They are universal.
Universal.
They demonstrated this predictive power across large language models, LLMs, native multimodal models, NMMs, and large vision models, LVMs.
That's stunning. Why is that so surprising? Couldn't we assume scaling laws would apply across different modalities?
You really couldn't, because the fundamental architectures and learning objectives are so different. I mean, an LLM processing discrete tokens is just a different beast from an LVM processing high-dimensional visual data. Showing that the same mathematical relationship between N, D, and H governs all of them suggests a deep underlying mathematical structure to how data domains interact at massive scale.
It transforms model design from an art into a predictive science.
It really does.
But this sounds almost too good to be true. How do you figure out the parameters of this universal law without running the costly large-scale training run you're trying to avoid in the first place?
And that is the efficiency breakthrough. The parameters of the scaling law, the constants and exponents that define its specific curve, you can accurately estimate them using only a few small-scale training runs.
Okay, so help me visualize this. You run, what, 10 or 20 smaller, cheaper training runs, varying the size and the mix. You use those results as data points to fit the universal curve, and then you trust that curve to accurately extrapolate to the massive scale you actually care about.
Precisely. You use cheap, tiny experiments to mathematically map out the landscape. The researchers showed that results from models under 1 billion parameters could be used to accurately estimate performance and find the optimal domain weights for models at 8 billion parameters or more.
And that's what their figure 4 illustrates, that leap of prediction.
Exactly. It gives practitioners a real, actionable alternative to the costly guessing game. If a company has a fixed hardware budget, a fixed N and D, this law lets them analytically calculate the optimal H to maximize their return on that immense compute investment.
This also seems to connect back to the limits we discussed in the reasoning section. If these laws are universal, could they also predict the point where a model's accuracy collapses?
Absolutely. The framework models the loss across the entire scale. If a certain complexity causes a sudden spike in loss, a failure, the framework has to account for it. So this could mean we can soon budget our compute not just for maximum average performance, but to specifically clear known complexity hurdles. That would make deployment far more strategic.
Okay, so we've covered the 4 pillars of fundamental research, from privacy math all the way to the economics of scale. Now let's look at how this all connects directly to practical deployment on actual hardware, which Apple demonstrated at the conference.
Right. The bridge between the research and the hardware is the MLX framework. This is their open source array framework, specifically designed and optimized for Apple Silicon. It's the engine that brings all this high-level math into the physical world.
And the optimization for Apple Silicon's unified memory architecture is the real key here, isn't it? For our listeners who might not be deep into hardware, why is unified memory such a big deal for ML?
In traditional architectures, you have separate pools of memory for the CPU, your main system RAM, and the GPU, which is VRAM. When you run large models, you're constantly having to copy massive amounts of data back and forth between them.
Which is slow.
It's a huge bottleneck. Unified memory solves this by allowing the CPU and GPU to access the exact same physical memory pool instantly, with no copying. MLX is built from the ground up to leverage this, letting you run models that need hundreds of gigabytes of memory incredibly fast on local hardware.
And they were demonstrating this live at their booth. Let's talk about the 2 demos that really highlight this. The first one was about mobile generative power.
Yes, the first demo was a clear, jaw-dropping illustration of local power. Real-time image generation from a large diffusion model running entirely locally on an iPad Pro with an M5 chip.
That's just phenomenal. We just talked about how resource-intensive diffusion models are. Running them in real time on a tablet, a battery-powered mobile device, is the ultimate proof of concept for the efficiency of MLX and these chips.
It moves what was a data center-only task directly into the user's hands. It really signals a future where local creativity and local privacy are the default.
And then they had another demo to push the boundaries of scale even further.
That's right, a massive distributed compute demo. This is where we connect back to Pillar 4, the science of scale.
What did that one involve?
They were showing text and code generation from a 1 trillion parameter model.
A trillion.
A trillion. And it was running inside Xcode on a cluster of 4 Mac Studios, each one with an M3 Ultra chip.
And again, the memory capacity is the critical detail here.
Absolutely. Each of those Mac Studios has a staggering 512 gigabytes of unified memory. That 1 trillion parameter model has weights that just wouldn't fit in the VRAM of a typical GPU cluster. This demo proved that by networking the immense unified memory of these M3 Ultra chips, they could efficiently house and run one of the largest classes of foundation models right there on the desktop.
Which makes this kind of frontier research much more accessible to smaller labs.
Exactly. And beyond the MLX demos, they also showed off a family of models designed specifically for efficiency with that framework, Fast VLM.
Mobile-friendly vision language models.
Right. These are designed to nail that accuracy-state trade-off on consumer devices, especially for high-resolution images.
And how do they achieve that balance? What makes it fast?
The innovation is in the hybrid encoder. They use a mix of a CNN, a convolutional neural network, and a transformer. CNNs are very fast at local feature extraction, while transformers are great at global context. By combining their strengths, they built an architecture that's super efficient at processing high-res images without the latency of a pure transformer vision model.
And the proof of concept for this was running on
The cutting-edge consumer hardware. Attendees could interact with a real-time visual Q&A demo running live on an iPhone 17 Pro Max.
So you could upload an image, ask a complex question about it, and get an instant, accurate answer.
Right on the phone. That's the final proof point. Taking complex research, optimizing it with MLX, and deploying it with instantaneous performance on a device in your pocket.
Finally, let's just touch on the community support aspects. A conference like NeurIPS isn't just about publishing papers.
No, it's not. And Apple reiterated its commitment to supporting underrepresented groups in the ML community, which is critical for ensuring the future of this field is diverse and inclusive.
They sponsored several important affinity group events there in San Diego, the Women in Machine Learning, or WIML, workshop.
On December 2nd, which is foundational for mentoring and promoting research by women.
The Latinx and AI workshop, also on the 2nd.
And, critically, the Queer in AI workshop and Evening Social on December 4th. This kind of broad engagement shows a holistic view of AI's future one, where technical advances are supported by a welcoming and diverse research community. So let's bring this incredible volume of research together. This deep dive has really explored 4 critical areas that define the frontier of fundamental machine learning.
We started with privacy, right? The mathematical elegance of achieving instance optimality while maintaining robust differential privacy, and how that improves model utility.
And we detailed how the theoretical guarantees of random allocation give you superior privacy utility trade-offs for large-scale distributed training.
Then we turned to reasoning, where that rigorous research with the puzzle environments exposed the illusion of thinking. The findings show that dramatic collapse of accuracy and that counterintuitive decline in reasoning effort at high complexity.
Which tells us precisely where the model's structural limits are.
Exactly. And then the creative leap in generative AI. We saw STARFlow successfully scaling normalizing flows to rival diffusion models at high resolution.
Giving us faster inference and that highly valuable exact likelihood modeling.
Plus the surgical precision of LinEAS for cost-effective, highly efficient activation steering using only a handful of samples.
And finally, the science of scale, where we learned that these universal scaling laws can now predict the optimal data mixture. That H factor for massive models across modalities using just a few small-scale runs.
It transforms model optimization from a high-stakes gamble into a systematic predictive science.
It does.
Which brings us to our final provocative thought for you to consider. The research has shown us that model design can be remarkably predictable through these scaling laws, letting us accurately forecast optimal performance with cheap, preliminary experiments.
Yet we also know definitively that when complexity surpasses a certain threshold, that point where reasoning effort paradoxically declines, even the biggest models fail dramatically.
So if we can calculate both the success and the failure points of massive AI systems with scientific accuracy, are we entering an era where model design is purely a science of predictive computation, removing human intuition from the process entirely?
Or does the nature of that illusion of thinking, that sudden, counterintuitive surrender to complexity, suggest that bridging the final cognitive gaps will always require an act of human architectural intuition that transcends the calculated parameters?
Keep thinking on that duality, the predictable science of scale versus the unpredictable nature of intelligence. Thanks for joining us for the deep dive.